Advanced Math, Lesson 90, double angle identities and half angle identities. So these are building up on the sum and difference identities that we should have pretty far memorized by now, mainly the first ones being A through D. And then we're going to be talking about the sum identities for sine of 2a and cosine of 2a. Now the way your book is going to ask you is quite literally just going to start asking you these questions over and over and over again. So pretty much all the questions found in Lesson 90, and you can go back and reference Lesson 90 by all means to look at those, because they just want to get you in the habit of understanding how the identities came to be, and it also helps gear towards memorization. So let's start with developing the identity for sine of 2a, and then we'll work on cosine of 2a. Now the key to this identity is we're going to use the sum identity. So in order to do sine of 2 times a, we have to understand that sine of 2 times a is equal to the sine of a plus a, right? Great, now we have a sum identity. From there we can take sine of a plus a and we can rewrite that, because we know that a plus a is going to be the sine of a times the cosine of a, and then that is going to be plus the cosine of a plus times the sine of a. Great. Now, once we, why am I so blurry? There we go. Hopefully you can see all that. Once we do all this, we realize that this second, whoa, wrong marker. Ooh, that could have been weird. We realize that the second coefficient, it can be written, any way around, because it's just two numbers being multiplied, and we know that it doesn't matter what order we put those in. So this can be rewritten as sine of a times cosine of a, still the same number. And what that lets us see is we have two of the same term being added together, which means we could simply rewrite this as 2 times sine of a cosine of a. Once we have that, we can undo the substitution, since we know that sine times 2a equals sine of a plus a. We can just resubstitute that back for sine of 2a. And now we have a double angle identity. The double angle identity is going to equal 2 times the sine of the angle times the cosine of the angle. So this is our double angle identity. This is how we create it. And that's for sine. Now let's go to cosine. Cosine is going to be the same concept. I went from green to blue. I'll go from blue to green in this one. So if I have cosine of 2a, I have to understand that that is equal to the cosine of a plus a, which is also a sum identity. That's going to equal the cosine of a and the cosine of a minus the sine of a times the sine of a. All right. From there, I just have to combine and square these. So this right side, cosine of a times cosine of a, is just cosine squared of a minus sine squared of a. And then I'll undo this substitution and replace this with cosine 2 of a. There we go. We just figured out our double angle identities. Super duper easy. Now, what's not so super, wait, do we do tangent? Do we do double tangent in this one? Oh, hey, we do. They do double tangent. Okay, hey, double tangent identity is super easy. We'll do this in red. All I'm going to do is I'm going to take this one, and then I'm going to put them on top of each other. This is going to be the numerator, this is going to be the denominator. I'm going to make a fraction. So I take 2 sine of a, cosine of a. I put that over cosine squared of a. Hopefully by now you know the reason why I'm putting these on top of each other is because the tangent of 2a is equal to the sine of 2a divided by the cosine of 2a. That's your basic tangent identity. Tangent is just sine divided by cosine. So that's all we're doing here. We're taking the sine of 2a identity, putting that in the numerator, the cosine of 2a identity, putting that in the denominator. Now the question is, how in the world can I simplify this? Honestly, we're just going to have to use complex fractions, and we're going to try to come up with a common denominator for both the numerator and the denominator. So the common denominator that we get here on the denominator, since this is a polynomial, is we have to pretty much, we want to get rid of one of these, so we're going to use cosine squared of a. So we put everything over cosine squared of a, cosine squared of a. What happens is this bottom then becomes 1 minus tangent squared of a. right? And then again, the reason why we're doing this in the denominator is to simplify it, and so we can make this an angle in terms of tangent. So pretty much what we're doing is we're looking for a way to cancel one of these and then create a sine over cosine scenario. So that's why we chose cosine squared of a, and why we didn't choose sine squared of a. Now if I do something to the bottom, I have to do it to the top. So I take the top of 2 sine of a cosine of a, and then I'm going to put that over cosine squared of a. Now the problem with this is I can't do anything. I can't cancel. Well, actually I can cancel here. Sorry, I don't know why I thought I couldn't do anything. I'm simply going to cancel one of these here, right? I cancel one cosine for the exponent, right? Because this is like 2 cosines, so I cancel cosine, get rid of the exponent, so now it's just cosine of a. So now this becomes 2 times sine of a over cosine of a, which is actually 2 times the tangent. So 2 tangent of a over 1 minus tangent squared of a. There we go. That is the double angle identity for tangent. That's a mouthful. Next on this lesson are the half angle identities. The half angle identities can be a little bit annoying, and it's because of a weird substitution they do. That weird substitution is, what's a good color for weird? Orange. Ha! Okay, so that weird substitution is this. We're going to be using the letter A, and in this entire problem we're about to do, A equals x divided by 2, or the angle divided by 2. So the unknown is the half angle, right? So just keep this in mind, but then put this off to a side because we're going to use A. This is the weird substitution. The reason why this is a little bit confusing is because of how it's presented in the book. So the way you do the half angle identities is we're going to start with these double angle identities, right? Or sorry, are we doing the double angle identities? No, hold on, sorry. 1 second, what are they doing here? Oh no, yeah, we are using the double angle identities. Okay, great. I didn't do that wrong. That would have been really bad. Okay, so we're starting off with the double angle identities, specifically cosine of 2a. Now that equals cosine squared of a minus sine squared of a. Now what we need to do here is pretty much solve each of these individually for sine or cosine, getting rid of the radical. So we'll split this off into 2 directions. Direction off to the left, we'll go ahead and we'll solve for cosine, because that seems a little bit easier to me. Yeah. Wait, no, I totally picked the wrong double angle identity. Okay, sorry, I just misread. I realized I misread what I was talking about. Scratch all that. Sorry. We're not starting with our double angle identity. We're starting by creating 2 new double angle identities. Man, okay. So we're not using this double angle identity. We're creating 2 new ones, and the ones we're using to create it are the cosine squared of a plus sine squared of a equals 1. We're using this identity to create both a cosine and a sine identity. We're doing this by solving for each of them individually. So for example, this problem, the cosine squared, if I wanted to solve, I want to first move sine squared to the other side. So now I have cosine squared of a equals 1 minus sine squared of a. To finish solving, I need to square root both sides. So I'll go ahead and wait, sorry, hold on 1 second. Yeah, okay, so now once I've got this value of cosine squared of a, what I'm going to do is I'm going to take this value and then I'm going to substitute it into the double angle identity. So instead of writing cosine squared of a, when I take this cosine of 2a double angle identity, which equals cosine squared of a minus sine squared of a, and I'm going to take this, I'm going to insert it right there. I'm going to substitute this value of cosine squared right in there. So now what I have is the cosine of 2a is equal to 1 minus sine squared of a in parentheses minus sine squared of a. What this becomes is, I have like terms here with sine squared of a, so what it actually becomes is 1 minus 2 times the sine squared of a. That's going to equal the cosine of 2a. From here, what I have to do is divide each side by 2 to get rid of the coefficient of 2. Right? So that now becomes cosine of a. Cosine of a is going to equal the cosine of A is going to equal 1 minus sine squared of A over 2. No, I did it backwards again. I just had to pause the video and double check because I was like, I feel like I'm working backwards now. I was. Half angle identities are tough. I'm not going to lie to you guys. So here I was trying to solve for cosine of A. I was supposed to switch and solve for sine. So the confusing thing about half angle identities is we don't start here. We start here. We solve this for cosine, and then we use that solved cosine to instead solve for sine. That's where I messed up. I forgot to switch gears down here and solve for sine instead. So I'm not going to divide by 2 because I think that also violates the inviolability argument because that's 2 times A. Yeah, it does. It breaks inviolability. I should have caught that. Okay, so let's go back up here. We have cosine 2A equals, I'm restarting from this line right here, 1 minus 2 sine squared of A. And what we're doing is we're actually solving for sine now because that doesn't break the inviolability argument. So I'm going to move the 1 over, so now I have cosine of 2A minus 1 equals negative 2 sine squared of A. Now what I can do is I can move this negative 2. Yeah, I can divide by 2, and that's not going to break inviolability. So we'll go ahead and divide each side by negative 2. So what that does is it gets me sine squared of A now equals, sorry, I got to rearrange all of this. The negative makes that positive, that can go away. And now what I've got is 1 minus cosine of 2A over 2. That is equal to the sine squared of A. From here, we take the square root of each side to get the sine of A, which is going to equal the square root of 1 minus the cosine of 2A over 2. And that is the half angle identity for sine of A. Wait, I forgot the last thing, the weird thing. This up here, this orange I put up here, right? So the whole reason why they do this whole substitution for A is because of all the pain you just saw me experience in doing this. And then from here, what they do is they substitute here and here. So now what this becomes is, let me write this in different color. I've been stuck with orange for a while. If I substitute x over 2 for A, this now becomes sine of x divided by 2 is now going to equal plus or minus, oh, I forgot to put plus or minus outside the square root, plus or minus the square root of 1 minus the cosine of x over 2. So it changes the whole thing because 2a, if 2a gets replaced with 2 times x over 2, 2's cancel, so it's 1 minus cosine of x over 2. So this right here is the half angle identity. I'm thinking, this was a lot of work. What I'm going to have you guys do is I'm going to have you start from right here. Yeah, this substitution. So when you guys have to do these half angle identities in your book, start from this substitution right here. Don't do the craziness up here. Yeah, start from this line and then continue on the proof. And the reason why I want to start from this line is so that way you go from substitute for cosine, solve for sine. So substitute for cosine squared, solve for sine. If you guys have any issues on this, which I'm sure you will, let me know on the school website and I'll see you in class.